All right, finally we get into the real meat of what chemistry is, right? When you think of chemistry, you probably think of, a mad scientist with bubbling beakers and, strange fogs and vapors and explosions and so forth. And so all of that is part of chemical reactions. So what is a chemical reaction? Well, simply, this is something that occurs, a process in which one substance is converted into another substance. Okay, this is different than like a physical change. Remember that a physical change is something that changes how a substance looks without changing what it is, right? So something like boiling water or melting an ice cube. It's still H2O in every case, right? You haven't actually changed what it is, even though you've changed how it looks. But in a chemical reaction, we are actually converting something into something else. So in the example shown here, we have methane, CH4, and we are reacting that with oxygen. And in the process, we're changing those. We're breaking some bonds, and then we're going to form new bonds in our products. Okay, and our products in this case would be carbon dioxide and water. So it's important to note a few terms here. One would be that we have reactants on the left-hand side of this arrow. Let me clear this out real quick. So you can see that we have this reaction arrow. All right, things that are on the left, we're going to say are the reactants, what we start with. Products are going to be on the right-hand side. It's also important to note that whenever you perform a chemical reaction, you are going to break some bonds in the reactants, and then you're going to form some bonds in the products, right? It's kind of like the old saying, you can't make an omelet without breaking some eggs. Well, you cannot have a chemical reaction occur without breaking some bonds and then forming some new ones. That's kind of the essence of what a chemical bond is. Or I suppose I should say that's the essence of what a chemical reaction is breaking those chemical bonds and forming something new. Now, this chemical equation that we've written out here is kind of a shorthand notation that tells us what's going on in a chemical reaction. So I've already mentioned where the products and the reactants are. I've shown you the reaction arrow itself. Now, a few things that you should note whenever we write a chemical substance. You're going to see some small numbers here. Those are the subscripts. That tells you how many atoms you have of each thing. So if I have CH4, the 4 here implies that I have 4 hydrogens. There's no number written here, but it's implied that it's a 1. So whenever there's no number, you can just assume that it's a 1. So we have 1 carbon and 4 hydrogens. So here we have O2. That means that we have 2 oxygen atoms chemically bound to each other. But you'll notice that in front of that we have this lovely little 2 that refers to the number of those actual molecules that we have. So those are the coefficients. And again, if it's not written, it's implied that it's a 1. So we could, if we wanted to, write in a 1 in front of the CH4 and a 1 in front of the CO2 to say that we have 1 methane molecule, 2 oxygen molecules, 1 carbon dioxide molecule, and 2 water molecules. And I put some antennae on there, and I could have myself like a happy little chemistry caterpillar. Anyway, okay, so whenever you see a chemical equation, you might see a couple of symbols. One thing that you'll always see would be the reaction arrow, okay, going from left to right, showing that the reactants are turning into products. Now, just some foreshadowing, we'll also see sometimes when you'll see a double arrow, which means that the reaction is reversible and can go either direction. A few more things that you might see, and this doesn't occur in all chemical reactions, but in some you might notice that you'll see this Greek letter delta, meaning heat. Okay, so that means that you have to heat up the reaction. You apply a flame or put it on a hot plate or something, kind of like cooking an egg, right? You have to apply heat to it. And then also, you might notice that on the bottom right-hand corner of some of the compounds, you'll see these letters in parentheses, either S for solid, L for liquid, G for gas, or AQ for aqueous solution, which means that the substance has been dissolved in water. Now, these will have absolutely no effect on how we balance equations and so forth, and so many times I'll actually just leave these out just to keep it from cluttering everything up. All right, but just be aware that if they are there, you'll see them in your textbook and so forth, and that's perfectly fine. It just tells us a little more about what's going on in the reaction, but it has no effect on how we balance it. So how do we know that a chemical reaction is actually taking place? Well, there are a couple of, kind of tip-offs that you should be on the lookout for, and these can help to indicate that something's going on and that you should investigate further. Now, none of these are actually proof that a chemical reaction has occurred, but again, it lets you know that something kind of fishy is going on, and maybe you should check it out. So some of these evidences would be a color change, right? Beaker suddenly, the liquid goes from green to blue. Something's probably going on there. A light emission, so think of a glow stick, right, or a firefly. There's a chemical reaction going on there. Gas formation, like a baking soda volcano, right? You add the vinegar, suddenly it bubbles up. I bet that we actually have a chemical reaction going on there. Also, you can have something known as a precipitate being formed. Now, what a precipitate is if you have a liquid, okay, inside of a beaker, and you go ahead and add some substances to it, and you might actually see some, kind of cloudiness occurring, and then you'll see the what we call the precipitate settling out. Okay, and so this here would be known as the precipitate. Okay, all right, and then this, remaining stuff that's dissolved would be known as the solution. That's why you can buy really lame chemistry T-shirts that still make me laugh, that say if you're not part of the solution, you're part of the precipitate, right? Because the precipitate is a solid that's in contact with the solution. All right, something else that you might see is either a release or an absorption of heat, right? So if you have one of those instant hot packs, like Toasty Toes or whatever you want to call them, where it suddenly warms up, there's probably a chemical reaction going on in there. But you'd have to, you'd have to actually check it out a little further, because it turns out that the only way to know for sure what is going on and whether or not it's a chemical reaction is to go in and analyze things at the molecular level, okay, to really see if we are changing one substance into another. And if we are changing one substance into another, then it's a chemical reaction. And if we're not, if we're just changing how things look, then it's not a chemical reaction. So let me give you some examples here. You tell me, is it a chemical reaction or not? Boiling water. Well, what do you think? Probably not, right? Because we have H2O to begin with, and so we still have H2O at the end of the day. So that is not a chemical reaction. It's just a physical change. What about burning firewood? Well, we had wood at the beginning, right, of the reaction here, and it's turned into soot and carbon dioxide. It's changed. And so that would be a chemical reaction. What about dissolving table salt in water? Well, taste the salt beforehand. It's salty, right? You taste the water with the salt in it. It's still salty. So we haven't actually changed what it is. We've just mixed the two together. So that's not a chemical reaction. What about the formation of rust on your car? Okay, well, it's going from iron into iron oxide or rust. So that is a chemical reaction or a chemical change. What about photosynthesis? So this is what happens when leaves take in carbon dioxide, and then they use sunlight to turn this into glucose and cellulose and so forth. So this is definitely a chemical reaction. We no longer have carbon dioxide. What about, you break up with that special someone, and she gives you back that Molde ring that you gave her, and so you decide to melt the gold and turn it into, I don't know, like a really expensive pair of fingernail clippers or something. Okay, that's not a chemical reaction, because it's still gold. It was gold at the beginning of the day, it's gold at the end of the day. So nothing's really changed there. So whenever we're talking about chemical reactions, one of the things that we're going to have to do is to balance the equations. You've probably heard this before, right? This is what most people think of when they think of chemistry, would be balancing equations. So balancing equations is really just applying something that we've already learned, which is the law of conservation of mass, which says that matter cannot be created nor destroyed in a chemical reaction. Now what we're going to say is that we're going to actually apply this to the atoms themselves. So we're going to say that the atoms cannot be created nor destroyed in a chemical reaction. So if I have, 10 carbon atoms at the beginning in my reactants, I have to have 10 carbon atoms at the end of the day in my products, right? So a balanced chemical equation always has to have the same number of atoms of each element on both sides of the reaction arrow. So what do I mean by this? Well, let's go ahead and take a look at this. I'm going to actually write in the ones here to show the coefficients. Okay, and I'm going to actually just go ahead and make a little table over here on the right hand side. So I have carbons on both sides of this reaction arrow. I have hydrogens on both sides of the arrow. And I also have, let's see, what else do I have? Oxygen on both sides of the arrow. So my job as a chemist for balancing equations is I need to go ahead and count the number of each. Okay, so here I have a carbon. There's just one of them. Okay, so I'm just going to say 1 over here. On the right hand side of the arrow, we also have 1 carbon. Notice that there are no subscripts written. It's implied it's just a 1. Now let's look at the hydrogen. Here I have 4 hydrogens, and notice that I just have 1 molecule of this, right? So I have a grand total of 4 hydrogens on the left hand side. Over here, it looks like I only have 2, but remember this the coefficient here of 2. So that means I have 2 of these water molecules, and so 2 times 2 hydrogens would be a grand total of 4 hydrogens on the right hand side of this reaction arrow. And then let's go ahead and check out our oxygen. It's the same type of situation. We have 2, but at 2 of those molecules. So 2 times 2 would be 4 oxygen on the left hand side. And then over here it's getting a little bit hairy, because notice that I have 2 oxygens there, and then over here for my water I only have 1, right? But it's actually 2 times 1 because of this 2 out front. So this 2 means that I have 2 water molecules, or in other words, I have a grand total of 4 hydrogens and 2 oxygens. So I have 2 oxygens here and another 2 oxygens here, so that gives me a grand total of 4 oxygens again. So this would be a balanced equation because I have 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side of that reaction arrow. So how do you actually balance a chemical equation? Well, there are a bunch of ways to do this, and it turns out there's not really any wrong way to do it. You kind of pick and choose the way that works best for you. So if you've learned a different method in the past and it works, then stick with it. Okay, but this is how I found that balancing equations works for me. The first thing I do is I remember go ahead and start with any element that I want. Okay, it really doesn't matter which one that you start with, as long as you kind of work your way through each and every element. And some people like to make tables to illustrate this, or whatever. Now, as you go along and practice with these, you'll find a couple of tips. Like personally, I always leave oxygen for the very end. I find that it's kind of a pain. It's all over the place in our chemical equations, so I personally leave it to the end. But you could start with it, and you could go ahead and figure it out from there, and that would totally be fine. The next thing you're going to do is go ahead and count how many of each of those elements you have. So I'm going to go back in and do that same thing that we did before. I'm going to make a nice little table here with hydrogens and oxygens, only 2 elements in our chemical equation this time. And I'm going to go ahead and start with hydrogen this time. So I have hydrogen here on the left hand side of the arrow. I have a grand total of 2 hydrogens there. On the right hand side of my reaction arrow, I also have 2 hydrogens. So far so good. I'm pretty happy with this. Now I need to go on and I need to go on to the next element. So notice that I have 2 oxygens on the left hand side of my reaction arrow, and I only have 1 over here on the right hand side. Because remember, since there is no subscript there, it's implied that it's just a 1. So I only have 1 oxygen on the right hand side. So this is not a balanced equation. So I need to do something about this, right? So what can I do to give myself 2 oxygens there? Well, you might be tempted to say, well, why can't I go ahead and, since I need 2, why don't I just change that subscript there and make it a 2. That seems really good, except it doesn't work. In fact, that's the worst thing you can do in a chemical, when you're balancing a chemical equation, is to change the subscript, okay? So never change the subscripts when balancing a chemical equation. All right, why? Well, it turns out there are two main reasons for this. One is that you change the chemical substance that you have. So for instance, H2O is water, right? H2O2 is hydrogen peroxide, which you probably have some on your bathroom cupboard. In a very dilute solution, it's perfectly safe, but the concentrated stuff is really deadly. All right. In fact, there's a bad chemistry joke that says that two guys walk into a bar, right? And the first one says, "I'm thirsty. I'd like an H2O, please." And the second guy says, "Oh, that sounds really good. I'd like an H2O too." And the second guy dies. So, do not ever change the subscripts, right? You change the chemical compound that you have. The second reason that you should never, ever change the subscripts is because every time you change the subscripts, a baby penguin dies. Okay? Well, at least now you'll remember it. Never, ever change the subscripts, all right? It messes up everything. So I'm going to go ahead and erase this because I cannot change the subscripts. So what can I do? Well, I can definitely go in and I can go ahead and change the coefficients. I can change the coefficients however I like. So I'm going to actually change the coefficient here to a 2. Because by doing that, it gives me 2 water molecules. Each water molecule has 1 oxygen in it, right? So that gives me a grand total of 2 oxygens. So notice that I now have 2 oxygens on each side of my reaction arrow. And everything seems great, right? But I should actually go back in and I have to continue to balance until everything's balanced. Notice that in the process of balancing the oxygens, I actually unbalanced my hydrogens, because how many hydrogens do I have on the right-hand side now? I actually have a grand total of 4 hydrogens on the right-hand side, because 2 water molecules, each water molecule contains 2 hydrogens, so 2 times 2 is 4 hydrogens. So what do I need to do over here? Well, I know that I cannot change the subscript, so the only thing I can do is to put a 2 out front to change that coefficient. So 2 times 2 gives me a grand total of 4 hydrogens. So by doing this, I've balanced the equation. And this one's a relatively simple one. We'll get into some that are a little more complex, but it's the same basic principle. Start with any element you want. Okay, never change the subscripts, only change the coefficients, and then keep doing it until everything is balanced. Once everything's balanced, you're done. So let's go ahead and try this with a slightly more complex reaction. All right, so in this case, what we're doing is we're burning C3H8. Okay, that's propane, and we're combining this with oxygen, so we're burning it, and we're producing carbon dioxide and water. You'll see these two products quite a bit because these are always the products of a combustion reaction. So what I'm going to do is I'm going to go ahead and draw my little table. When I'm doing these, myself, just for fun, I don't actually write out the table because I don't, feel like I need it. But when you're starting out, it seems especially useful just to make sure that you have everything. Okay, so I have my carbon, hydrogen, and oxygen. Now I'm going to go ahead and start with carbon. You could start with any of them, but I'm going to start there. So notice that I have a grand total of 3 carbons on the right-hand side. And over here I only have 1. So what do? Do I change the subscript? No, because baby penguins would die. So instead I'm going to change the coefficient. I'm going to put a 3 there. That gives me 3 carbons. Now my next task would be to look at my hydrogens. I have a grand total of 8 hydrogens here. I only have 2 here. So what coefficient can I put in front in order to make that come out to be an 8? Well, I can put a 4 there because 4 times 2 would be 8. So that would give me 8 hydrogen there. So the only one that's left is oxygen. Now notice that this is a little complex because we have so many oxygens all over the place. So over here I only have 2. and I have a nice blank spot right here in front that I can go ahead and put in anything I want to make that multiply out to the number that I desire. So notice here with my water, I have 4 water molecules. If it helps you, you could actually write a 1 there to see that 4 times 1 would give me 4 oxygen here, and then 3 times 2 gives me 6 oxygen here. So I have a grand total of 10 oxygen on the right-hand side of my arrow. Alright, what about on the left-hand side? Well, I only have a 2 there, but if I put a 5 in front, 5 times 2 gives me 10. And so now you can clearly see that this is a balanced equation. I'm going to go ahead and just erase all this extra gunk here, just so that we can see what's going on with this reaction. So this is how I would write it. C3H8 plus 5O2 plus, yields 4H2O plus 3 CO2. If you really wanted to, you could put a 1 there. It's not wrong. People just don't usually bother doing it. But if it helps you to kind of see what's going on, that's perfectly acceptable to put a 1 there. Alright, so far so good, right? Not too horrible. Let's go ahead and try another one. And in this one, I'm going to show you a little trick that I find useful. Okay, you might do this a different way, but I think it's kind of a useful technique. So here I have aluminum and chlorine, okay, my 2 elements. I'm going to go ahead and start with the aluminum, and it looks like I have 1 aluminum on the left and 1 aluminum on the right. Perfect. It's already kind of pre-balanced for me. Now, the next thing I notice is that I have 2 chlorine on the left and 3 chlorine on the right. This is a problem because there's no whole number that I can put in front of the Cl2 to make it come out to be Cl3, right? I would have to use like a 1.5. And when you're balancing an equation, for style reasons, we don't use fractions. Because if you really think about it, it doesn't make sense. I can't really have like 1.5 chlorine molecules. I either have 1 or I have 2. I can't have 1.5. So fractions don't fly when we're balancing equations. So some people do a lowest common multiple and so forth, and they kind of figure it out from there. What I like to do personally when I'm balancing these things is I like to, if I run into a situation where I have an even odd number, kind of like how we have here, even odd, I go ahead and I double everything that I've already balanced. Okay, so I already balanced the aluminum, so I'm going to put a 2 here, and I'm going to put a 2 here because I already balanced that. Now, why did I do that? Well, for one thing, it kept all of my work complete. Right? It didn't mess anything up. So notice that I still have 2 aluminum on the left and 2 on the right, so that the aluminum is still balanced. But now what has it done to help me out? Well, notice that I have 2 times 3 is 6 chlorine on the right-hand side of the arrow, and so I can definitely work with that. I can put a 3 here, and 3 times 2 would give me 6 chlorine on the left. And so that's the nice thing about this little trick about doubling everything you've balanced, is it keeps things balanced so that you don't have to go in and like redo an element, but it allows you to to work with this until you get the right number. So if that helps you, roll with it and use it. If not, then don't worry about it. Alright, so we're on a roll here, so let's keep going. Let's see what we have here. It looks like in this case we actually have photosynthesis going on. Let's go ahead and use green for our lovely little leaves here. So what's happening? Well, we have carbon on both sides, we have hydrogen on both sides, and we also have, I get so excited about the oxygen that I'm trying to throw it in all over the place. Okay, so we also have some oxygen here. Now, in order to balance this thing out, let's go ahead and look at the carbon. Notice that on the right-hand side here we have 6 carbon, which means we're going to need 6 carbon over here to balance that out. Okay? Now, what about our hydrogen? Notice that on the right-hand side we have a grand total of 12 hydrogen. So we're going to need something over here. So, let's see, so 6 times the 2 would give us 12 hydrogen. So remember, you're always multiplying the coefficient times the subscript. in order to get the total number of atoms for each element. Okay, now for the oxygen, the tricky one. Okay, this thing again is all over the place. So let's go ahead and try to figure this out. What do we have here? Well, we have 6 times 2 giving us a grand total of 12 oxygen. Here we have 6 times 1 giving us 6, giving us a grand total of 18 on the left-hand side. Right? What do we have on the right-hand side? Well, here there's only a 1, right, for our coefficient. So that would give us a grand total of 6 there. And then we don't have a number written there yet, but whatever it is, it's going to be times 2, right? So I'm going to actually write in 2x. And I know that this right-hand side needs to equal 18. So you could either do the guess and check method, or you could go ahead and solve for, solve for x here. And let's see, it looks like x has to equal 6, right? So if I go ahead and put a 6 out front here, then 6 times 2 would be, a grand total of 12 here. And so that would be 18, and that's perfect. So that gives me a nice balanced equation for photosynthesis. Okay, and now for one of my personal favorite reactions. It's the production of nitrogen triiodide, which you should totally Google this thing because this stuff is pretty amazing. Contact explosive that's perfectly stable when it's wet. You could hit it with a hammer and nothing would happen. And yet when you actually allow it to dry, it becomes so sensitive that even like a butterfly landing on it would set off the explosion. You get this big explosion, a puff of purple smoke. Lots of fun for pranks. Illegal to make in Italy, so don't do it there. But small amounts can be lots of fun. The reaction is actually much more complicated than this. This is just kind of a simplified version of it. But let's go ahead and try this thing out. So we have nitrogen on both sides of the arrow, and we have iodine on both sides of the arrow. Okay. Now, what do we want to do? Oh, we also have some hydrogen on both sides of the arrow, correct? All right, we need everything in there, otherwise this thing just will not work. Okay, so let's go ahead and start with nitrogen. It really doesn't matter which one we start with. Looks like we have 1 nitrogen on both sides of the arrow. So far, so good. What about our iodine? It looks like we have 2 iodine here and 3 iodine here. So what do? We have this even-odd conundrum. Well, remember that we're going to double everything that we've already balanced. We already balanced the nitrogen, right? So I'm going to put a 2 in front of the nitrogen here and a 2 in front of the nitrogen here. So by doing that, notice that I've kept my nitrogens balanced so that I don't have to go back in and rebalance them. But I have a grand total of 2 nitrogens on both sides of the arrow this time. So that's good. What have I done with my iodine now? Well, I have 2 times 3, giving me a grand total of 6 iodine on the right, which means that I can put a 3 here, and 3 times 2 would give me 6 iodine over here on the left. Now notice that it's also fixed my hydrogen problem, because that one also was even and odd, or odd and even, I guess, in this case. And so here we have 6 hydrogen on the left. So what can I put over here? I can put a 3, because 3 times 2 would give me 6 hydrogen on the right. Right, not too bad to balance this thing. You can celebrate by going on YouTube and Googling nitrogen triiodide and checking out a couple of really fun videos there. Okay, only one more balancing equation, and then we can go ahead and move on to the rest of the section. So let's take a look at this one. This one might be a little trickier than others. I'm not sure. We'll find out, right? And we have carbon, hydrogen, and oxygen. This is another combustion reaction. Notice that we're producing carbon dioxide and water. This one's actually the burning of ethanol, or drinking alcohol. So if you've ever had a nice flambé dessert, this is what's happening. So while they're flambeing it, you could go ahead and write this equation out on a napkin and impress people. You try it and let me know what happens. Okay, so what do we have? Well, we have a grand total of 2 carbons on the left-hand side, let's go ahead and put a 2 in front of the carbon on the right-hand side. That balances the carbons for us. What about our hydrogens? Well, we have 5 here and 1 here for a grand total of 6. Okay, what about over here? Well, we only have a 2, so 3, oh, there we go, 3 times 2 would give me 6 hydrogen on the right-hand side as well. Okay, I'm going to go ahead and just clean these up so that we can work on the oxygen, because the oxygen is going to be a bit of a beast this time. So we'll actually even just change our color. Nice soothing blue color. Okay, so how many oxygen do we have in our equation? Well, we have 1. Here we have 2, but we could go ahead and put any number we want in front of that. So I'll call that 2x. Okay, over here we have 2 times 2 gives me 4. And here 3 times 1 gives me 3. So on the right hand side I have a grand total of 7. Okay, so I'm going to actually just move this over here, but it looks like on the left hand side we have a 1 plus 2x, and we need it to add up to 7 in order to have 7 oxygens on either side of the arrow. So you could go ahead and just plug and chug and guess away. You could crunch it using some algebra. Turns out we could go ahead and do a 3 here, right? Because 2 times 3, 6 plus another 1 gives me 7. So it looks like my missing number there has to be a 3, which would give me a grand total of 7 oxygen. So this one's really not that bad. The only tricky part you have to remember is that notice that we have oxygen here and here and here and here. So oxygen is showing up all over the place, which is again why I like to leave it for the very end. But you can go ahead and do it at the beginning and balance it at the beginning. I find it a little more difficult that way. So that was a little tricky, but we're done with the balancing equations for now, and now we're going to take a step back and talk a little bit more about what's happening in our chemical reactions and what types of chemical reactions do we have. Well, the first term that I need to define for you is dissociation, which is the separation of anions and cations when you put an ionic compound into water. So think of putting table salt into water. The sodium and the chloride ions will actually dissociate. They'll break apart from each other and they'll start floating off into the water itself. So this happens with KCl here, potassium chloride. Notice that it's a solid, and now we have aqueous, or dissolved in water, potassium and chloride ions. Notice that the same thing happens with sodium sulfate. Here we have 2 sodium ions that go floating off, and then we also have a sulfate. One important thing to notice is that this sulfate does not break apart from itself, right? It dissociates from the sodium, but the SO4 2 minus, the sulfate ion itself, actually stays together, right? So that's an important thing to remember, is that polyatomic ions do not break apart, okay? It wouldn't break apart into a sulfur and 4 oxygens. Okay, it doesn't work that way. So polyatomic ions stay together as a single ion, even though they will dissociate from the other ions that they are attached to. Very important thing to remember. Now, when we're talking about dissociation, it's important to talk about electrolytes, right? You've seen Gatorade commercials where they say, oh, it's chock full of electrolytes for maximum hydration. All they really mean is that it's salty, okay? They put a lot of salt in Gatorade. Electrolytes are just substances whose water solutions conduct electricity. So you could actually run a current through the Gatorade and it would work, right? Growing up, my mom always said, oh, you got to stay out of the water, like swimming pools and so forth, when there's a thunderstorm, because water is a very good conductor of electricity. And unfortunately, that's false, all right? Water is actually a really horrible conductor of electricity. It's an insulator. But as soon as you dissolve any kind of salts or ionic compounds in the water, then it becomes an electrolyte solution, and then it becomes a very good conductor of electricity. So if your swimming pool was full of just pure distilled water, it wouldn't be such a big deal if lightning struck one end or if someone threw a toaster into it. You'd still be fine. But once you have those chlorine salts in there, once you start to sweat and so forth, there's always going to be some kind of dissolved salts in there. And then you got to watch out for the flying toaster into your swimming pool. Now, a couple of quick definitions. Some compounds are soluble, which means that they dissolve in a specified liquid. So we say that they're water soluble, or that they are, soluble in hexane and so forth. And then insoluble compounds don't dissolve, or they dissolve to such a tiny amount that it's not really noticeable and we don't worry about it. So how can you tell if something's going to dissolve? Well, the easiest thing is to use what's called the empirical method, which means you put it in water and you see if it dissolves, right? And if it does, then you write a little check saying, yes, it dissolves in water. And if not, then you put a little X that no, it does not dissolve in water. It's insoluble. But you don't always have access to a full chemistry lab and all of the ionic compounds that you could desire. And so therefore it's important that we follow a set of rules that's not perfect, but it predicts pretty well when something will be soluble and when it will be insoluble. So these are the solubility rules that I want you to remember. All right, they're relatively simple, and again, they're not perfect, but they work pretty well. So the first thing we're going to say is we're going to, whenever we look at an ionic compound, we need to look at the cation, right, the positive ion, the ion that's listed first, to see if it's one of these ones. If that ion happens to be lithium, sodium, potassium, or the ammonium ion, it will automatically be soluble. There are no exceptions to this rule, okay, or none that you should worry about. So anytime you see lithium, if it's lithium chloride, lithium phosphate, lithium hydrogen carbonate, it does not matter. Okay, you can automatically assume that it's soluble. Now, what if the cation is not one of those listed? Well, then we move on to the anion, and it's not the end of the world. So we're actually going to look at the anion, and if the anion is the nitrate ion or the acetate ion, then again you can assume that it's automatically soluble. It doesn't matter what it's paired up with. It doesn't matter if it's calcium nitrate, strontium nitrate, aluminum nitrate. It's automatically soluble in water. All right, what if it's not one of those? Well, if it's one of the halides, these halogen ions here, so chloride, bromide, iodide, then it's typically soluble, but there are a few exceptions. Okay, if it happens to be paired up with silver, mercury, or lead, then it's not going to be soluble. So something like, strontium chloride would be soluble. Silver chloride, not soluble, right? So if it's a chloride, bromide, or iodide, check and see if it's one of the exceptions. If it's an exception, it's not going to be soluble. Otherwise, you can assume, for this course at least, that it's going to be soluble. Same type of thing applies when you hit the sulfate ion. Sulfates are typically soluble, but not if it's calcium, strontium, barium, or lead sulfate. Okay, if it's one of those, it's an exception. So let's actually try this and see if we can figure out which of these compounds will be soluble in water. All right, so the first thing we're going to look at would be the cations, right? And if we happen to see one of these cations, then we automatically know that the compound is soluble. So notice here we have sodium, okay, sodium hydroxide. Sodium salts, soluble. Ooh, here's potassium bromide. Potassium salts, soluble. So I'm circling it. Anytime it's soluble, I'm going to go ahead and just circle it just to illustrate that. And then things that are insoluble, I'll just put a little line through it. Okay, do we see any other lithium, sodium, potassium, or ammonium? Going down the list, I don't see any that contain those cations. So we have to keep going. Let's look for nitrates. Do we have any nitrates there? Oh, yep, we've got lead nitrate, automatically soluble. I don't see any other nitrates in the list. What about acetates? Nope, no acetates here. Okay, what about chlorides? Oh, here's a chloride. Okay, it's paired up with calcium. It's not paired up with silver, mercury, or lead. It's not one of the exceptions. It's soluble. Okay, oh, here's another chloride. Oh, but this time it is paired up with silver. Okay, so that's an exception. That will not be soluble in water. Okay, no, I don't see any bromides or iodides on the list. Let's move on to the sulfate. Oh, here we've got sulfate. Okay, it will be soluble unless it's paired up with calcium, strontium, barium, or lead. Oh, in this case it happens to be paired up with barium, therefore insoluble. Barium sulfate's the stuff, the nasty kind of slurry that you have to drink when you go in for a GI x-ray, And if you've had one of these before, it's kind of a nasty, like drink, because it's all chalky. And what's happening is that the barium sulfate won't dissolve in water. So it's actually a suspension, which is why they shake it up before they give it to you. And so you drink that, and the barium is opaque to X-rays, so they can image your GI tract. And because it's not soluble, the barium ions don't go into your body, which is a good thing because barium is actually pretty toxic. So if the nurse was looking through the cabinet and said, "Oh, we're out of barium sulfate. I'll give the patient some barium nitrate." Well, barium nitrate dissolves very nicely in water, and you would be dead from heavy metal poisoning. So make sure it's barium sulfate. All right, so what's this last one that we have here? The last one we have is calcium carbonate. Notice that calcium is not listed as one of our cations here, and then carbonate's not listed as one of our anions here. Since neither the cation nor the anion is listed, we can assume that it will be insoluble. And in fact, calcium carbonate is limestone, so it's definitely insoluble. It's a good thing because most of Washington, D.C., all the monuments and so forth are made of limestone, and if they were soluble, every time it rained, it would dissolve. And then the government would be like, "We need to rebuild this monument." And then they'd probably rebuild it out of limestone, and we'd run into the same problem again and again. Okay, so now that we've actually looked at solubility, we can understand why some things will precipitate out of solution. Remember, we've mentioned this previously, but a precipitate is an insoluble solid that's formed when you react two chemicals, they exchange ions, and then you end up getting something that won't dissolve in water. So here's an example. Notice that here on the left-hand side of our arrow we have potassium iodide that's aqueous and lead nitrate that's aqueous. So those will both dissolve nicely in water. Now in the process of dissolving, the potassium is going to pair up with the nitrate, and the lead is going to pair up with the iodide. So it's kind of like they mix and mingle, swap partners here. And now we have potassium iodide, which is aqueous, but we also have lead iodide. So potassium nitrate and lead iodide. Potassium nitrate stays in solution, but the lead iodide will actually form a precipitate. And in this case, I believe it's bright yellow. But you get this precipitate that will form in the solution and kind of crash out of solution. It turns out that lead compounds are very brightly colored usually, and they're cheap, which is why they were often used for lead paints. So if you live in an old house, you should get it tested for lead paint because it can be a major problem, especially for young kids, because they'll put anything in their mouth, right? So they find a little paint chip or something and they eat it, and then they're like, this is good, because it turns out that lead compounds are typically sweet, and so it's like candy. It's like Willy Wonka, and you're like peeling candy off the wall and eating it, and it causes brain damage. So you should definitely get checked for lead. Okay, and if you see anyone licking the walls, you know something's up, and you should probably get it tested for lead. All right, so now that we understand about precipitation reactions, what about acid-base neutralization reactions, or just neutralization reactions for short? Well, it turns out that when you take an acid and a base together, they will neutralize each other, right? They kind of cancel each other out. So you can see in the reaction, for a generic acid and base, they'll always form some kind of salt, some kind of ionic compound, and water. So the easiest way to recognize one of these acid-base neutralization reactions is look at the products. If you have salt and water, then you have a neutralization reaction. Now again, salt just means some kind of ionic compound, although it could actually be regular table salt. In fact, let's say that you're making some fries, you've got some friends coming over, and you ran out of salt, right? Table salt, sodium chloride. And so you think, you know what, I could make some sodium chloride here. I don't want to have to go all the way to the store and buy it. So you could take some hydrochloric acid and some sodium hydroxide, which is Drano, and you can mix those two together. And then you'll actually produce water and sodium chloride. You could evaporate the water, and suddenly you've got salt that you can sprinkle all over your tasty French fries. The only problem is if you happen to have any leftover sodium hydroxide on there, that will actually turn your mouth into soap and it will bubble away. So I do not recommend actually doing this. It's a really bad idea. Just go, get off your lazy butt, go to the store and buy a little salt shaker and call it good. But you'll notice that this is a neutralization reaction because we have an acid and a base. They're making a salt and water. Now we can see in this next one, similar reaction. This is actually, baking soda and vinegar. All right, so looking at this one, we actually have vinegar here and baking soda. This one's an acid, this one's a base. We mix those together and we make a salt, an ionic compound, in this case sodium acetate. And then also notice that we made water, right? So we made salt and water just like before. Now in this reaction we also happen to make some carbon dioxide, which just bubbles away, and that's why your baking soda volcano actually erupts, is because of the carbon dioxide bubbles. So in an acid-base neutralization reaction, you may have a gas produced, oftentimes you do, but the main thing to look for would be salt and water. We can actually classify chemical reactions in a couple of different ways. One way is to classify it based on the actual process that occurs. So we've already mentioned precipitation reactions, in which you get a solid that's formed, kind of looks like a snow globe in your test tube. You get this solid precipitate forming. We've also mentioned that you can get acid and base reactions, in which case you produce a salt and water, okay, in a neutralization reaction. Now, many acid-base reactions are also gas evolution reactions, which just means that you're producing, gas bubbles in the reaction. And then also we have another class of reactions called oxidation reduction or redox reactions. So you'll often hear this term, redox, and it stands for reduction oxidation or oxidation reduction. Now in this case, what's happening is you're actually transferring electrons from one compound to another. Now, one subset of these oxidation reduction or redox reactions would be combustion. We actually balanced a couple of these. This is typically what you'll see is that you are taking your reactant, some kind of fuel. It could be propane, it could be magnesium, whatever. You're taking your fuel and you are going to go ahead and combine that with oxygen, and then you are going to make water and carbon dioxide, right? So, this would be a typical, combustion reaction, and you'll see these quite a bit. But besides classifying these chemical reactions in this way, we could also classify them based on what the atoms themselves are doing. And this is probably an easier way to do it. So we'll go through each of these, but there's synthesis reactions in which you're combining things, decomposition in which you're breaking them apart, single displacement in which you're kicking out one partner, and double displacement in which you are mixing and mingling and switching both partners. So let's go ahead and look at these general equations for classifying our reactions and see if these make a little more sense, instead of me just mumbling about it. Now we'll go through some examples of each of these, but the general form for what's happening in a synthesis reaction is you are synthesizing something, right? You're taking two or more substances and creating something new out of it. Decomposition would be the opposite, right? You're taking something and then breaking it apart into its component pieces. In a single displacement, we're just going to have A come in and kick out B, so that B is all by its lonesome now. And then in a double displacement, this is where the two chemicals come in and they're actually going to mix. So A is going to pair up with D, C is going to pair up with B, and now you have new compounds. You might have recognized this from our precipitation reaction with lead a little earlier. So let's look at a synthesis reaction. These are sometimes called composition or combination reactions depending on who you talk to, but in any case, what you're doing is you're taking two or more reactants, combining them to form a single product. So notice in every case we have something like magnesium. Back up for a second. We have something like magnesium coming in and combining with nitrogen to make a new compound, magnesium nitride. Same type of things happening with our carbon monoxide and oxygen, we are forming one new substance. Again, two things coming in, forming one new substance. All right, so a synthesis reaction. Now a decomposition reaction would be the exact opposite of this. This is where we are taking a single component, in this case like water, and if you run an electrical current through water, you'll actually produce hydrogen gas and oxygen. It's kind of a fun little experiment. You can throw a 9-volt battery into some water, especially salt water, and you'll see some bubbles forming. You can trap those bubbles, light a match, and you'll get a little pop, and it's a decomposition reaction followed by a synthesis reaction when you reform the water. We can also take mercury oxide here, like Antoine Lavoisier did, and we can actually break that down into liquid mercury and oxygen gas. So let me show you a quick example to try to illustrate the difference between these two types of reactions. So I have here some wintergreen lifesavers. I love wintergreen lifesavers. One of the reasons is because they taste good. The second reason is because they exhibit something called triboluminescence, which means that if you take a couple of these into a dark room, especially like a bathroom, so that you can look in the mirror, turn off all the lights, let your eyes adjust, and bite down on a couple of these wintergreen lifesavers, you'll actually see little flashes of light, triboluminescence. It's cool. Anyway, so I'm going to use these to actually illustrate the difference between a synthesis and a decomposition reaction. So I'm going to go ahead and pull out a couple of these tasty lifesavers. I'll try really hard not to eat them. They do have to be wintergreen lifesavers if you want to see triboluminescence, though, because of the oil of wintergreen, the methyl salicylate that's in there. All right, so you can see I have two delicious wintergreen lifesavers here, and if you watch closely, you can actually do a synthesis. You can take two of these, combine them into one, right? Just like this. Kind of fun. All right, and then decomposition would be the opposite. This is where you actually take these things apart, and now you have individual ones, and the best part is you can actually eat these afterwards. That's my favorite kind of magic trick. Okay, so now that we've seen synthesis and decomposition reactions, let's go ahead and take a look at single displacement reactions. Remember that in a single displacement, this is where one atom is actually going to come in and displace another in a compound. These are sometimes called single replacement reactions in some textbooks. But what's happening is, notice that zinc is going to come in, it's going to kick out the copper in this case. And so now copper is off by its lonesome over here. The same type of thing happens in this reaction here, where aluminum comes in, kicks out the iron. So iron's all alone. This is actually known as a thermite reaction. You should Google that. There's some pretty cool videos about it because it's so exothermic that we actually produce molten iron in the process. Fun little reaction. All right, and then here we have sodium coming in, and it's going to kick out some of the hydrogen. So notice that hydrogen's off by itself, and we've made sodium hydroxide in the process. Now, if you can have a single displacement or a single replacement reaction, you can also have a double displacement or double replacement reaction, in which case both compounds are actually going to kind of mix and mingle, and they're going to swap their chemical partners here. So in this first case, notice that we have magnesium hydroxide and hydrochloric acid. The magnesium is going to come in and partner with the chloride. Hydrogen is going to partner with the OH. So now we have magnesium chloride, and then H plus OH makes H2O, water. Same type of thing happens in our next reaction. Barium is going to pair up with the sulfate, potassium pairs up with the nitrate. We make barium sulfate and potassium nitrate. And then in the last one, lithium will pair up with nitrate, and silver pairs up with chloride. Now, in these reactions, you might be asking yourself, why in the world does lithium partner up with nitrate, but lithium won't partner up with silver? Well, remember that lithium has a positive charge. Silver also has a positive charge. Chloride has a negative charge, and nitrate has a negative charge. So in this case, if lithium's floating around looking for someone to hang out with, it's going to be attracted to either the chloride or the nitrate. It will never be attracted to the silver because they both have a positive charge. And so If it partners up with the chloride, then we just have our lithium chloride, like in the reactants here. If it partners up with the nitrate, then we form lithium nitrate, like in our products here. You'll also notice that these reactions can be classified in different ways. So this top reaction was an example of an acid-base or a neutralization reaction. Also, we're labeling it as a double displacement reaction. So, we can classify these in different ways, and it really depends on kind of what you're trying to get at, what you're trying to explain about the reaction, depending on how you're classifying it. Now, let's go ahead and just classify a couple of reactions, and then we'll finish up. So, what do we have here? Well, our top reaction, we have two things turning into one product, right? So that has to be a synthesis or combination reaction. So that would be synthesis. In our second reaction, we have carbonic acid breaking down into water and carbon dioxide. So one reactant turning into two or more products. That must be a decomposition reaction. Okay. In our next reaction, we have potassium hydroxide and hydrobromic acid. Notice how the potassium is partnering up with the bromide to make potassium bromide, and H plus OH is making our H2O. So in this case, we're swapping both partners. This must be a double displacement reaction. And then you can probably guess that the last one must be single displacement, because that's the only one left, and I'm obviously going to give you an example of each. But just to be sure, let's see what's going on. Magnesium's coming in, kicking out the iron to make magnesium chloride, and then we have free iron sitting here all by itself. All right, so that sums it up for this section. Thanks for bearing with me.